I'll be hosting today's discussion, as Julieta was saying, and I've got a number of people joining me today. First of all, from Frost Sullivan, we have, let me move on there, we have Sundarya Govashankar. Sundarya is an industry principal in my chemicals team, and having been with our company since 2007, her research recently has focused on the opportunities being created for chemical companies from the energy revolution, everything from materials for the hydrogen economy to bio-based feedstocks and, of course, battery materials. Sundarya completed our competitive benchmarking report, which we call our Frost Radar, on battery material suppliers in June of this year. And at present, she's just wrapping up our new market forecast report on the battery materials market as well. And joining her and myself, we have a fantastic panel of guest speakers today too. First of all, Stefan van Vickeren is industry marketing specialist for energy storage and generation in Daikin Chemicals. Daikin is one of the global leading fluoropolymer companies, and Stefan is based in their innovation center in Dortmund in Germany. Stefan works across two areas for the battery market, PFAS-free developments, and also on new technologies for batteries such as solid state and dry processing using PTFE. Tim Anhan is a senior business developer at Leidenjar, a company that is developing silicon anode technology in the Netherlands. Silicon anodes have the potential to increase the energy density of batteries tremendously. Leidenjar is currently focused on scaling their technology again in the Netherlands, and one of the key target markets for them is consumer electronics, where the goal is to enable devices that are even smaller and more powerful than they are today. And finally, Jackson Briggs is the Manager of Strategy and Business Development for Draslovka, the Czechia-based global leader in hydrogen cyanide and derivative chemicals. Draslovka is producing Prussian blue analog anode and cathode materials for sodium-ion batteries. Jackson brings a transdisciplinary perspective with a background working in small, medium, and large businesses, and experience working on every continent in a wide range of capacities. So, thank you all for joining me for today's discussion about what's going on in the battery materials space. And first of all, I'll hand over to our expert in Frost & Sullivan, Sundarya, to present a few slides, first of all, on the research we're doing. And after all of the speakers have presented, we'll go into an open panel discussion between us as well. So first of all, Sundarya, over to you.
Thanks, Bran. Hello, everyone. Thanks for joining us on this webinar today. It's a pleasure to be a part of this event. So Frost & Sullivan has been tracking the battery materials market for several years now, and across various dimensions also. We have our mobility team tracking the batteries going into EVs, and we have an energy division that focuses on batteries going into stationary applications. We have a tech vision team that captures all the technology trends, IP, patent-related things in the battery landscape. We, Brian and I, are from the Chemicals and Materials division from Frost & Sullivan, focusing on material trends. So earlier this year, like Brian mentioned, we completed a benchmarking exercise, competitive benchmarking exercise for battery materials, where we plotted various companies based on growth and innovation indices and discussed the competitive aspects in the space. So we're now wrapping up a full-blown research with market forecasts and trends covering lithium-ion batteries, sodium-ion batteries, and solid-state batteries, the materials that go into in there. So here is a small scope slide on what we're covering in the report. So we are covering anode, cathode, electrolyte binder, separator materials, as well as additive sealants used in batteries. So we noticed that in addition to these, there are several other materials that are significantly important in the battery, within batteries, that could include coatings, foams, films, laminates, or polymers that are used. So what we'd be doing is we'd look at the growth opportunities that exist for these materials too. We'll not go in detail doing a forecast for these materials. And we also focus on different applications like mobility, stationary, consumer electronics that are actually presenting varying demands in terms of battery capacity or energy density or charge retention characteristics, lightweighting, miniaturization, etc. So this also covers regional trends, like it's shown here. So yeah, this is pretty much the the scope of the study. Can you move on to the next slide, Bran? Just to provide a quick summary or snapshot of the findings from the report, I thought we would show the strategic imperatives and growth opportunities for different companies that exist within the battery materials ecosystem. So by ecosystem, I mean they just don't necessarily relate to the battery material companies, but also the other stakeholders such as the AI companies or battery manufacturers, automotive OEMs, or technology providers that may exist in the market. So the study will have more growth opportunities covered from other perspectives also, but we thought we will discuss about a few things here. I will get to the growth opportunities in a minute, but looking at strategic imperatives. First, they are essentially the megatrends that are creating a change in the industry, and these might also be the risk factors that the stakeholders need to be aware of. So first of it being geopolitical chaos, with a lot of critical raw materials being concentrated in specific geographies, and regional policies in the US and Europe, specifically trying to reduce material dependence on China. They are leading several changes in the industry, such as the supply chain localization or evaluating and testing new materials, new chemistries. So the move towards silicon anode is one such move, though it is also because of performance reasons, but and another factor that aids in silicon anode transition is the dependence that these regions get for the supply of graphite from China. But we've also been seeing a lot of investments that are supported by tax incentives and grants for silicon anodes in this space. So similarly, another key megatrend that the battery material market is looking at is the PFAS and the regulations around PFAS and other solvents like NMPs. That are basically affecting the binder and electrolyte formulation. So this is driving stakeholders towards PFAS-free formulations, and in some cases even binder-free electrodes. So material innovation, new product development are also becoming a part of crucial compliance, but and also about competition. So from a competitive standpoint, in order to be tackling issues around supply chain volatility, establishing partnership opportunities, regional capacity expansions are all becoming very important. So we'll be discussing on most of these points later in the webinar. So coming to the growth opportunities, the first one being more about the we presently see a lot of anode cathode chemistries that are being developed to suit specific battery types like Prussian blue cathodes or layered oxide for sodium ion batteries or silicon anodes for lithium ion batteries, etc. But going forward, developing chemistries that can be used across battery platforms will open up greater opportunities. For example, we came across a company called LionVault that has come up with a 3D lithium metal anode architecture that it claims to be compatible with lithium ion, sodium ion, as well as solid state batteries. Next, talking about repair and recyclability of batteries. So batteries are moving towards modular and easy to dismantle designs. There is a lot of trend towards repair, recycle, and reuse. We have the right to repair legislations in the US and the proposed eco-design law for smartphones and tablets to have user replaceable batteries. So we will see a lot of opportunities for resealable adhesives or debondable adhesives within, as we move towards easy repairability. I will reserve the growth opportunities 3 and 5 for later discussion with the panelists. So I will go on discussing the fourth growth opportunity, that is around leveraging AI for speeding up processes across battery value chain. So material development often involves trying and testing millions of combinations and ratios, but generative AI has proven to be helpful in sifting through the vast material combinations that are available to identify the right material that will effectively deliver the required characteristic properties. So real-time quality control using machine learning tools, yield maximization, predictive maintenance, and process optimization can all be achieved by AI. However, gaps do exist in the fact that AI tools are mostly used in isolation, and a material that happens that appears right in theory is impossible to synthesize at scale, or it could happen that it is more expensive or unstable in real world scenario. So integrating AI with a complete ecosystem where AI predictions lead to automated synthesis and testing will be crucial. So there are companies like Aonics that are bridging this gap of integrating AI-driven processing and battery material ecosystem, helping development and commercialization processes. So this is about the strategic imperatives and growth opportunities that we came across the study so far. Moving on to the next slide very quickly. I have represented the key battery materials.
Sorry, Sundaria. And yeah, just we got a lot of material to get through today, so maybe just a 1-minute summary of this one quickly, and then we can move on.
Yeah. So we do have. So we already see since penetration chemistries. Silicon anodes are gaining momentum rapidly, and we are expecting to see faster commercialization, faster adoption levels during the forecast period, like midterm up until 2030 and beyond. While sodium ion and solid state battery chemistries are mostly in development, pilot stages, planned commercialization, etc. So we will see that these materials like layered oxide, Prussian blue cathodes, hard carbon anodes, lithium metal anodes are being developed in the during from between 2025 to 2030. But if you look at lithium metal anodes, we see there is a lot of integration between companies are mostly integrated to produce both anodes and electrolytes, and there are also anode free architectures where anode is being built in situ during the process. So these are some of the highlights that I wanted to show. So you could move on now, Brian.
Right.
That's from my
Great. Thank you, Sundaria. So we'll allow each of the speakers to present themselves now about their own technologies before we have a panel discussion afterwards. And the first panelist I would like to invite to speak is Tim, about their work in Leidenjar. So Tim, over to you.
Thank you very much, Brian, and thanks for inviting me here. Yes, my name is Tim Aanhane. I work at Leidenjar in the Netherlands, and we develop pure silicon anodes, a new battery technology for the market. Well, in this next slide, indeed, we can look at why we are developing new battery technology, because it's never about the next battery. It's never about actually launching a battery in the market. Batteries power all kinds of applications, from automotive to consumer electronics, and there the innovation happens that needs to be powered with new battery technology. If we look, for example, at this consumer electronics industry, the applications there demand new batteries, whether that would be wearables, fitness trackers, smartphones, or these augmented reality glasses. These innovations in this electronics industry are quite exciting, but are limited by the batteries that power them. If we look at the wearables, they need to be smaller to fit on your wrist, or smart rings, or even comfortably wearing augmented reality glasses. These require very small batteries. But still, these batteries need to be very powerful, need to have a high capacity, to have the AI on board of your smartphone, or to add more fitness tracking sensors on your smartwatch or smart ring. That's an even more demanding of the batteries that we have now. And then ultimately, it requires a local supply chain, so that every new device that needs to be developed will also have a supply chain either in the US or in Europe or in Asia, where the batteries come from. Well, the problem with the current batteries that we use is that they cannot power this revolution, whether it be the AI revolution or the fitness tracking revolutions. The batteries that we have today are limiting that growth. Now let's dive into what's the problem. Next slide, please. In the battery, we have the cathode and the anode. And the anode, the negative side, is practically always made from graphite. It has been a great material in the last 40 years of powering all our battery devices because it can store energy pretty well. But the problem with graphite is that we're storing energy in graphite to its theoretical maximum. We practically cannot store more energy in graphite. So if we want to increase the capacity of a battery, we have to make the battery bigger. And that's not practical for these wearable devices or our smartphones. Graphite is also a scarce material, and it's very polluting to mine it. And more than 90% of all the graphite gets mined and processed in China. We're fully dependent on China there. Well, we already know for a very long time that there's an alternative material to graphite as anode material. It is silicon. The great benefit of silicon is a great holder of energy. It can store 10 times the amount of lithium ions. It's also very abundant. It's the second most element on Earth. And you can practically mine that on every continent. So it's possible to have a local supply chain and to process it locally. So if it's such a great material, why aren't we using that in all our batteries? Well, the problem with silicon is that it swells, it expands when you charge it. And we need to find a solution for that. Next slide, please. If we use silicon instead of a graphite anode, well, silicon can store 10 times the amount of energy. So the anode gets 10 times thinner. You see that the battery gets a lot smaller. So you can make smaller batteries with the same amount of capacity, or add multiple layers of these anodes and cathodes, and thereby create the same volume of the battery, but with a higher capacity. You can increase the battery capacity by 50% by using a silicon anode, pure silicon. And that is what Light & Jar developed and produces. It's the anode foil. You see it here in the middle. It's copper foil with pure silicon on there, and it can store energy very well. Now, I already said that silicon expands, and that's why we couldn't use it so far. If you use silicon in a normal process, in a normal battery process, it will just expand, fall apart, and break your battery. So this silicon anode that we developed is actually enormously engineered to actually mitigate the swelling within the material itself. It has a porosity, so that swelling happens in there, and it doesn't break. Next slide. We produce that using a process we borrowed from the semicon industry. Light & Jar is based in the Netherlands, close to companies like ASML, NXP, and Philips. And we took a semicon process to make this silicon structure. The silicon structure then can swell within itself, and it keeps very strong and tight and doesn't break. It uses a PECVD process, plasma enhanced chemical vapor deposition. This is a semicon process. It's actually a lot simpler than how anodes are used today, and it uses a lot less energy. So it's the breaking process for the battery industry, which we're now trying to scale. We're scaling that in the Netherlands. It's a more sustainable process and makes this silicon anode. And we're planning to scale that further into Europe to the big global market. Next slide. Currently, we are producing with pilot production in the Netherlands, in Eindhoven. And we're producing these rolls of this material, which we can ship to battery makers all over the world. For example, in China, they are now making tens of thousands of batteries with this material, just taking the roll of a silicon instead of a roll of graphite and making the batteries in the same way. In 2027, we will open our first production facility, also in Eindhoven, and that will all be focused on producing this silicon anode for the consumer electronics industry. Because with this silicon anodes, we can make these batteries even smaller and thereby have the biggest value for the anodes that we produce. By the end of the decade, we will further scale this process, scale this equipment that we make ourselves, and also focus more on automotive.
Drozlowska, so if we hand over Jackson to you and to tell us about your technology.
Thanks, Brian. Yeah, we've ordered the presenters here perfectly because I think I have a lot of the same themes that Tim touched on, but on the cathode side instead of the anode side. So let's jump into it. Next slide. So Drozlowska, we're a global leader in chemistry for critical materials. Based in Prague in Czechia, we have manufacturing both in Czechia and the US, and a major footprint in Mexico, South Africa, and Australia as well. So we're the leaders in hydrogen cyanide chemistry in the world. And that might sound like an exotic thing, but one of the great things about hydrogen cyanide is the raw materials that go into making it. It's very common materials, caustic soda, ammonia, and natural gas. And that'll be really important as I get into talking about why Prussian blue analogs and sodium ion cathode technology is so important to the battery value chain. So currently we are scaling up our production capacity for sodium ion anode and cathode materials. We have about between 150 and 300 megawatt hours of capacity currently at our plant in Czechia, with the flexibility to expand that by between 5 and 10 times as the demand for those technologies grows. And we have the flexibility also to produce material to a wide variety of specs. As Tim highlighted, there's more and more battery technologies that are being developed and are maturing and being commercialized. And I think we're moving more towards a world where there's going to be more sort of fit for purpose technologies and less of sort of the monolithic landscape that we have today with lithium ion. And part of that growth trend is going to be driven by the ability to scale up and produce those technologies at commercial scale. Next slide. So Prussian blue analogs. This technology has an enormous potential to power the future battery supply chain. So sodium-ion batteries have been around just as long as lithium. Lithium-ion performance surpassed sodium pretty quickly and got a lot of the attention from the last several decades. Sodium-ion didn't get as much investment in development as lithium kind of took the stage, but over the last few years with lithium price volatility, there's been a renewed interest in sodium-ion technology. And so where we sit today is it's a segment that has competition between a few different cathode materials, a few different technologies. So why sodium-ion technology over lithium-ion? Well, like I mentioned, price volatility of lithium in particular and the markets for the critical minerals that go into the current lithium chemistries like cobalt, nickel, and manganese. We've seen, especially in the last 12 months, an increase in sort of geopolitical focus on these materials, and there's sort of a political football globally between China and other countries they trade with. So one key, I think, goal for new technologies needs to be supply chain resilience, so that battery producers can be sure they'll have the product they need to make their end product. And then cost competitiveness is another key part of the sodium-ion value proposition. Again, with lithium prices being very volatile, hitting some pretty high peaks a few years ago, that sparked renewed interest in other chemistries. And with sodium being as abundant as it is, it's a much more the raw material markets for its inputs are much more stable than they are for lithium-ion batteries. So the three contenders on this landscape within sodium-ion technology, as Sundarya mentioned earlier, layered oxides, polyanionic materials, and Prussian blue analogs. So Prussian blue analogs are what we're focused on. And if we could go to the next slide, please. Okay, so between these three technologies, layered oxides, so these are layered oxides of metals like it could be as common as manganese or as exotic as something like vanadium. Polyanionic compounds, these tend to be iron-based, phosphorus-based. They may have some other elements in there as well. And then Prussian blue analogs is what we're working on, which is really a critical mineral-free chemistry. So the raw materials that go into this are what I mentioned before, common feedstocks made from common elements like carbon, sodium, nitrogen. So things that are highly abundant across the world, but also that we have production of across the world. So Prussian blue analogs excel with that supply chain flexibility and also cost competitiveness and I would say cost stability. So because those materials are so common, they trade on highly liquid markets. You don't see the same volatility and input costs that you do in lithium-ion and lithium-ion chemistries. And so it's going to provide a much more stable environment for downstream producers to utilize this technology and have more predictability and more confidence in their operations. So cost is something that's going to continue to improve across all these technologies as production methods evolve. We're in the really, really early stages of the game with sodium-ion technology. As more producers scale up production, they're working on developments to reduce those costs. Tim alluded to the dry electrode processing. There's a lot of other really interesting technologies out there that will continue to drive down cost across all technologies, but also in sodium ion specifically. So what Draslovka is working on, we're working to close the gap in, which you can see on the charts down here at the bottom, that scale-up availability. So Prussian blue analogs are dependent on HCN chemistry. Cyanide is a scary word to a lot of people. It can be a scary chemical. And so production of this has been very regulated, somewhat limited worldwide. But with the right capacity in place in the right places, there's no reason why we can't scale up the battery materials that utilize hydrogen cyanide chemistry and produce them at the scale that the world needs to continue to develop the battery value chain.
Right.
So we'll talk more about some of those points later, but Brian, I think we can move on.
But Stefan, if we hand over to you to talk a little bit about what Daikin is doing in this field as well now.
Yeah, thank you, Brian, for the short introduction, and thank you for the invitation to present Daikin today. Yeah, I'm responsible at Daikin for the energy storage sector, and firstly, I want to introduce quickly Daikin in general. So as Brian already mentioned, Daikin is one of the leading fluoropolymer supplier in the world. So we are producing fluoropolymers and other fluorochemicals, which you can find in more or less every department of your daily life. So in life science, chemical and oil, but also in the new advanced technologies like semiconductors and especially also the energy solutions where I'm part of. So next slide, please. Globally, we are active in different research centers. So in Japan, Osaka, in China, in the United States, but also in Europe, we opened our new innovation center 2021, which should act as a key driver to track European trends in Europe, and especially for the energy storage. We have a decided area for battery and also hydrogen economy. Next slide, please. If we're talking about batteries and our products, one of the key drivers we are seeing currently in the industry is our PTFE. And this technology is really promising because this enables dry electrode production in advanced production state. So it's a massive upgrade compared to the wet process. And on the next slide, please, we can already see some of the advantages, Brian. Yeah, next slide. Yeah, thanks. So one is, for example, that we don't need any solvents anymore. And Tim already highlighted that as well. So this solvents is NMP, which is an SVHC, which is toxic and can really be detrimental in the process. Moreover, due to the dry process, you don't need any drying line, which is one of the main cost drivers in state-of-the-art manufacturing for energy consumption, but also on the capex potential, for example. And this, in the end, also highlighting that you don't have any solvent material reactions, which are also enablers for example, for next generation batteries. So dry process can be also integrated in all other upcoming technologies, so in solid state battery concepts, but also sodium-ion batteries, for example. So on the next slides, we are also highlighting here some new areas which we are elucidating in our innovation center in Europe. And this is because of the key trend in Europe on PFAS-free batteries. PFAS regulations are really important. And this is meaning that Daikin is really highly interested into finding new PFAS-free binder solutions for the battery infrastructure. For example, with an NMP-free process, aqueous processing can be one candidate. And for that, we are eager to look and find new alternatives in our innovation center. And on the right-hand side, you can also see our activities in the next generation polymers regarding solid-state battery concepts. So one could be dry process, but also other polymerization technologies like in situ polymerization or also gel-type electrolytes can be a crucial role in future. So these two additional parts are key application areas and innovation areas we identified for Europe and we are working on in our innovation center. And that's from my side. So thank you for your patience and looking forward for a great discussion with the other people and also hopefully can answer some of your questions. Thank you.
Yeah, absolutely. Thank you, Stefan. So yeah, no, really interesting to see what all three of you are doing to develop technology further in the space, as batteries will be more and more needed in the future, obviously. And I've got 4 questions that I wanted to run through with you all now today. As Stefan just mentioned, again, anyone in the audience who would like to ask a question, you can do so in the Q&A. But if anyone who's listening would also like to reach out to any of the speakers individually after the briefing, their contact details will be in the slide deck that we'll be sharing after the event as well. So please do reach out if you're interested in talking further with ourselves or any of the speakers today. So the 4 questions I wanted to ask today, we'll get the opinion of everybody on all of these. And the first question I wanted to raise was looking at the simple perspective of material innovation and how material innovation does drive performance enhancement in batteries. So Tim, maybe we'll start with you and your thoughts on that.
Yeah, absolutely. Well, you can look at a battery in a very different ways regarding its performance. You can look at the performance based on the capacity or the power, safety, sustainability, or costs. And every application, every market looks at these performance metrics in a different way. I think I'll leave the cost factor probably to Jackson. He has a good view on that, what's needed there. But if we would look at the capacity, for example, of the batteries, in the last 10, 15 years, we haven't seen an enormous increase in battery capacity. Approximately 2 to 3% per year, the batteries went up in capacity, because there has only been incremental innovation on the material side. If you keep using the same materials, you'll practically get the same capacity out of it. And all the components contribute to that. For example, the cathodes, there's been some incremental innovation on the cathode side, mostly benefiting to sustainability and costs, with a focus more on LFP, reducing the cost for batteries. And on the anode side, there hasn't been a lot of innovation. So there we're looking for very new anode materials like either silicon or silicon graphite, but also lithium metal or completely anode-free cell designs, where the anode can really contribute to higher battery capacity and higher battery energy density. On top of that, there's innovation on next generation electrolytes, additives, or as very new production processes that also can contribute to all these metrics. But mainly a point that I want to make is that we're looking at the complete battery system. So we can't only see the silicon anodes or LFP cathodes or a new process as a solitary innovation. It should all fit into one system which works together. And we'll have to look at the whole system, how that get benefited from these new innovations. So any company that says, well, we have a drop-in solution or it works with everything that's available in the market, I would be a bit skeptical about it. And every new technology should be viewed in the complete system.
Yeah, Stefan, yourself?
Yeah, I can only agree to Tim. So in the end, it's you need to see what is your application, and what do you need from your battery. So is it a really safe battery? Is it a high energy density battery, and so on. And then you need to select your material and you need to optimize it. And for example, for silicon, the electrolyte is playing a key role. So if it's a solid state electrolyte, next generation electrolyte, but also electrolytes which create a really fluorinated interface is really important, for example. So these parts need to be considered as well. So you always have to look the broad picture, I would say. And this is the key to drive material innovation in the industry, I would say.
Jackson, any final thoughts from yourself on this?
Yeah, so I think between the three of us panelists, I think we're a good representation of just how many new technologies there are out there. And as Stefan pointed out, I think, as I said before, we're entering a world where there's going to be a wider proliferation of different battery technologies for different purposes. But at the end of the day, you can have fantastic performance in a product, but you have to be able to make it, and you need to be able to make money off of it. And I think that's a key area of innovation for us across the value chain. And as companies working together to build out these products, is that collaboration between suppliers to be able to make the materials available to actually produce these technologies. You can make a battery out of a potato, or you can make a battery out of something like tin or vanadium, but you need to have the availability of the products that go into making them. You need to have these really specialized materials, specialized components. And so I think, really us as a battery ecosystem kind of looking at the supply chain differently and partnering with companies that have similar targets is going to be key to getting these products off the ground in the future. Moving away from the sort of monolithic landscape where everyone's making very similar sort of components on a very large scale to maybe partnering with companies that have a very clear vision of a product market fit and being able to take those products to market and grow sustainably over time.
No, great. Thank you, Jackson. Second question I wanted to bring up then was looking at the big regulatory changes happening either today or possibly coming in the future that will influence what you do for the battery market. And I guess there are a couple of obvious ones that we've already talked about, but just wanted your views generally on the regulatory trends that will be affecting this market. And Stefan, if we maybe start with you this time.
Yeah, for sure. Yeah, I can definitely answer that from a European perspective. So regularity perspective in Europe is a really, really key trend for the battery industry. I think one of the main drivers is the battery passport regulations regarding different parts of the battery need to be considered and regulated. For example, also recycling quotes and so on to keep the industry in Europe. So this is one part. Critical Raw Material Act is one part, I would say, which is also really important. And for sure, also new trends like PFAS regulations, which are PFAS discussions. So how they are affecting in the end the battery industry. And for example, on that, I can also tell about initiatives from Daikin that we are part of substitution groups for PFAS in batteries, for example, on the European Union level. We are part of Horizon projects finding PFAS alternatives for batteries. So we are really eager to find these new materials. So we are prepared for the next times, I would say, and being prepared for regulation steps from the European Union, for example.
Tim, you've come off mute. Do you want to offer your perspective there?
Yeah, absolutely. Well, also based in Europe, but also relating that to the US regulation, see most of the regulation either being focused on a local supply chain or on sustainability. Luckily, most of the new companies and new technologies have that in their strategy. Should be part of a business plan to have a sustainable local supply chain. And then these regulations can either help, but also have some downsides. Can help in getting the supply of the critical materials, can help in getting electricity or a place to build your factory, and also can really help in getting the right funding. But regulation can be slow as well, slower than a scale up wants to grow. And if then lots of extensive audits on is this really sustainable and do we really need this here, can actually slow down a process. So it can be very helpful, but we should also accelerate some of these processes together.
Yeah, thanks, Tim. Obviously, we'll come on to the whole topic of critical raw materials and supply chain next, but looking at this regulatory trends, Jackson, your thoughts on that?
So I know we'll get to that topic later, but I don't think you can talk about supply chains without also talking about regulations in the mining industry and what's happening around the world with mining of the critical minerals. There's a high-profile lithium project in Europe that was basically canceled or put on the back burner yesterday, and we're seeing more and more of these major projects that were expected to meet raw material needs being sidelined due to social pushback or regulatory pushback on the mining industry. And so I think that highlights the need for technologies and a battery value chain that has the resilience and sort of the composition to avoid major disruption from those sort of upstream factors that we've seen time and again over the last several years, whether it's been in nickel or whether it's been in lithium or other minerals that are so important to current battery chemistries.
Before we move on to the next question, Daria, was there a perspective you wanted to offer here as well on the regulatory side?
Yeah, from the regulatory perspective, we have been tracking the regulations across several industries, and we identified PFAS to be the most important ones in the recent times. And we did a dedicated report sometime last year, and we'd be soon updating that. So it is definitely very critical to look at PFAS and companies trying to find alternatives. So I think anode binders, we have the market has moved towards CNC and SBR polyacrylic acid chemistry several years back. But I think it's for cathode binders, especially for NMC, that PVDF continues to be challenging. So there are waterborne binders that are being developed. Companies like Lanke, Freer, Northvolt, they're all coming up with water-based binders for LFP cathodes. And Northvolt is also looking at completely phasing out PFAS-based binders using bio-based aqueous and the company technology with its new carbonics provides PFAS-free, NMP-free binders for cathodes. And as Stefan mentioned, Daikin is also working at into alternatives. So it's a clear trend that companies will have to come up with alternatives wherever there are fluoropolymers. Yeah, I just wanted to add that part.
Yeah, no, thanks, Daria. And so if we do move on now, look at the whole topic of critical raw materials strategy, supply chain security, localization, etc. These are having a huge impact on the battery industry. So you wanted to get the view of each of you on how this is impacting the market today. And Jackson, we talked about lithium versus sodium, lithium mining you mentioned, but generally, what is your view on critical raw materials and supply chain security here?
Sure. Well, like I mentioned before, I think it's critical, especially for new technologies coming to market, to have predictability in supply chain, not just in price, but also in availability of those materials. If I look at here in the U.S., the landscape over the last 5-10 years has been for the battery cell producers and end product producers has been really strongly dictated by this need. The most high profile example would be Elon Musk constantly tweeting people to add lithium processing capacity, or putting his comments out there as to where the weaknesses are in the supply chain. But again, I think it underscores the importance in new technologies, not just to focus on materials that will be available so that those products can reach their end users downstream, but also that there's collaboration between suppliers across the whole value chain to ensure the capacity is there when it needs to be, and there's a really strong sort of strategic alignment between those companies and those partners, rather than it just being sort of an opportunistic approach.
Great, thanks, Jackson. Tim, your thoughts on the supply chain issues?
Yeah, what if we look at the supply chain of these end markets? The supply chain of EV, of consumer electronics, where do they get their batteries? More than 75% of all the batteries are produced in China. More than 95% of all the graphite anodes are mined and produced in China. If you take the entirety of Asia, the numbers go up even more. So we have a full dependency on Asian countries for all these batteries for electric vehicles. But later on, also for humanoid robotics, electric aviation, all these other markets that are emerging, they will need to get the batteries there. And we'll need to get some independent supply chain to get the battery production up here as well. But we don't, in my opinion, need to take that completely over to Europe or to US. We don't need to make all the batteries ourselves. As long as we get a valuable position in the production of batteries, whether that be on sodium-ion technology, whether it be an anode technology, or some specific processes to make the cells. If we get a relevant position in that market, in that value chain, we can have a more balanced supply chain and get a better trade position.
Right. Thanks, Tim. And Stefan, yourself?
Yeah, I also agree. So I think the dream of 100% supply of batteries from Europe or something like that, this is over. So this China free or whatever free supply chain, I think this is really challenging, but we need to consider that we have some critical applications where we need to be independent in the end. So, for example, defense applications. I think for that it's a key to be independent from other regions of the world, and this is also something we need to consider. This is also something the European Union already understand and consider now in some future regulations maybe as well. But in the end, yeah, I totally agree. We need material innovation, we need process innovation to get a piece of this cake, but the broad of the share will stay in Asia, will stay in China. This is already clear.
And Sundaria, finally, yourself.
Yeah. So, like all the panelists mentioned, there is a clear move away from China for material independence, but strategies could differ depending upon the material and the type of battery component that we are looking at. But the foreign entity of concern rules in the US, they I think limit the qualification of the $7,500 tax credit for Chinese, North Korean, or Russian entities control more than 25% of manufacturing. So this is compelling the need to get more supply independence. So if you look at the case of graphite, China dominates 95% of anode production, and like many of you pointed out, global graphite prices have declined 10 to 20% in the recent times, but US costs will still surge on Chinese imports. So US and Europe are investing in silicon anodes, not just for independence, but also for performance of batteries. But it would aid significantly in tackling the material independence as well. So we see a lot of investments happening in those lines. And if you look at LFPs, China again has a very dominant position, and we have seen that Morocco has emerged as a destination to build the Western LFP manufacturing capacity due to strong phosphate reserves, US-Morocco free trade agreement making products IRA eligible, and geographical and political positioning. But however, we've noticed that in the recent times, many Chinese battery makers have announced investments in Morocco since the IRA has been passed. And this suggests that Chinese companies might be using Morocco as a backdoor entry into the US. But so it is very interesting to look into the battery supply chain and the whole industry to see how the geopolitical dynamics are playing and how supply chain localization will actually be achieved in the process.
Cool. Thanks, Sundaria. And the last question I wanted to bring up was, when you look at all these interesting new technologies being developed for the battery industry, there is the big question of scalability, and if there is to be perhaps a balance between performance gains and manufacturability at scale. If I could take, I don't know if any one of the panelists wants to go first on this one, but sort of question to all of you on that.
Maybe I can start. So I think scalability in the end is a key. So we already saw that from Northvolt, for example. So where quality of the electrodes were not good, where maybe some scalable issues are there. So you see from big hopes and big increase in performance, or some better advantages of the products. You see if it's not scalable, and if you can't scale the production in the end, then you will never produce batteries on a commercial scale and on a productive and cost efficient way. And this is, I would say, a key, and will be a key, to be cost efficient, to make money in the end, because otherwise nobody will do that. And this is really a key trend. But also, scalability is not meaning that we don't getting any performance increase in future anymore. So this is really the key, that we are developing new materials which are easy to scale in the end, processes which are scalable. So for dry process, we see this challenge, for example, that the scalability is not at the same level like the classical wet process, but we are working on that. Our key customers are working on that. And I think we are now on a good way that we will see dry processing on a scaled production with some watt-hours in near future in Europe, in United States, but also, honestly speaking, in Asia as well. So this is in the end really important: scalability, cost efficiency, but also to be performant in the end.
Jackson, yeah.
Yeah, so I'll highlight, China's been more successful than any other country in the world at scaling batteries. And part of that is because they have a sort of a unified approach to the supply chain. They see what components are needed for a technology, and they're very well coordinated in putting capacity online, on time, and where it needs to be able to produce those products. I mentioned it before, but I'll say it again. I think collaboration between partners along a particular value chain is really important. And I think it's moving away from an opportunistic mindset and moving more towards finding partners that have enough incentive to sort of commit to a product, commit to a technology over a longer period of time, but also have the right specialties, rather than trying to find the cheapest inputs from a commodity producer for whom it may not be that important, because it's whatever product it is a tiny fraction of their overall revenue. Moving towards more sort of specialized partners that have more stake in the game on these technologies. And so I think there's so many great battery technologies out there, great ideas, but it's really that collaboration and that coordination that's going to determine whether they sink or swim in the market.
And Tim, finally, yourself?
Yeah, if you would combine those two views, which I both fully agree with, I see that it's maybe an obvious answer, but both scalability and that benefit in performance, you both need them. Otherwise, you have no chance of doing anything in this market. The experience and the scale of the current players in the market, the big battery manufacturers, you can't overcome that with only scalability if you don't have any benefit on performance. The incremental innovation already happens at companies like Samsung SDI, LG, ATL, CATL. They're all doing the small steps every year, and they have the scalability that you cannot beat with a new company. You need to have the scalability in the product, in the process, in all the partnerships, in the ecosystem. You need to have that, and an enormous gain in performance, so that you can actually get the investments, get the time to further scale this. I don't think it's a problem if you cannot scale it this year or next year. If it will be happening in 5 years or 8 years from now, it's fine. But the scalability should be inherent in your process, in your product, and the benefits as well. And that will give you the opportunity to set something up in this market.
Thanks, Tim. And sorry, Jackson, were you going to ask?
I'd just like to echo a point that Tim made earlier. When we talk about performance, because the focus has been so much on EVs in the battery world over the last 10 years, a lot of times people equate performance with energy density. But I think it's important to think about that in other terms as well, whether it's cycle life or charge discharge speed, and that's key to being able to develop and commercialize this diversity of different technologies we have coming online. It's not just focusing on that energy density piece, but focusing on sort of the full spectrum of benefits that these technologies can bring.
No, absolutely.
Sorry to respond on that. I experienced firsthand that for a long time the EV manufacturers, they focused on increasing the range to remove the range anxiety and get to a 1,000-mile car battery. Now it's not about 1,000 miles; it's about 100 miles and low cost, low weight, and get these EVs on the roads on an affordable basis.
Yeah, and I guess there you've got that divergence between urban cars and cars that you'd be happy going on a grand tour around Spain in or something like that.
Yeah.
But to come back to your point, Jackson, that was the question I was going to ask. And Tim, you mentioned this whole need to look at the wider ecosystem. And if there is to be a step change in energy density in batteries, then there'll also need to be a step change in terms of the charging speeds, whether that's in actual minutes you need or simply the number of kilowatts you can put into the battery. So does that need to be an important part of the consideration, is collaboration with the charging infrastructure companies, or just understanding what charging speeds might be needed for these higher capacity batteries?
question was to Jackson, right?
To whoever feels like they can offer an opinion on it, I guess.
Yeah, I think I'll just echo my previous point. Collaboration across the whole value chain is important. That's why the industry looks like it does today, with so much so much market share and so much attention being on China. And I think it's important for everybody across the value chain to understand that they are one piece of the puzzle, and that collaboration upstream and downstream for everybody is important, not just in product development, but also on strategic planning and making sure there's alignment and kind of commitment to rolling those new technologies out.
And final question, a year or two ago, maybe it seemed like one of the big issues in the market was still looking at the fire hazards that came with batteries, whether it would be in consumer electronics or in cars as well. And do you feel like that's still an issue and something that's really important to take into account when developing new technologies?
Absolutely, that's still an enormous challenge, especially as we're pushing for higher energy densities. Battery cells beyond 500 amp hour we've seen. The risk of short circuit and extreme hazards is always around the corner if we're looking for new materials and new higher performance.
And I'll just say that's not one of the benefits that I've touched on, but it's one of the key benefits of sodium-ion technology, sort of across the board, is that virtually eliminating that risk of thermal runaway that lithium-ion chemistry has. So I would say we have the solution already. It's just a matter of implementing it where it needs to be implemented.
Stefan, any kind of final thoughts from yourself?
So safety is key. So you see it, zero propagation strategy. Also, if you're considering maybe new pack design, so instead of cell to module, that it's going to cell to pack, cell to chassis, whatever design. So this is also always considering safety in the end. And without a safe battery, you will not sell a battery. But also to mention here, batteries are already really, really safe. So if we are comparing the fire rates of a combustion vehicle compared to an electric vehicle, you see that it's way lower than the combustion vehicle. So this is also something we should highlight maybe in the society, that battery electric vehicles are safe, because we are doing so much in the material innovation to keep it safe and to have safe batteries in the end.
Right. No, thank you, Stefan. So no, thank you for the discussion, everyone. Yeah, great to hear you talking about how, for example, collaboration is key. I'll take that away. New application I hadn't thought about previously for batteries, which I really need to think about in the research we do next year, which is robots, obviously. So we'll be looking more at that next year as well. But